not on because we need to start with the light
It's
off.
not on.
And as a matter of fact, it doesn't matter where the data taking process, there is no light as long as there is some fraction of time with no light.
Okay.
The order in which you like you forget it, oh man, the light was on. No big. Go there, turn it off for a while, count some Mississippis and then turn it back on and you're good to go. Right?
Okay.
Good. So now, and this is where it gets important, the data lives in a folder called data, holds APMPs, and don't forget that this Linux has a continuation, so if you type the beginning of some address and whatnot and it knows it and you push tab, it's gonna give it to you. So for instance, I put a capital E and tab is gonna tell me, oh, there are two of them, buddy, which one you like? We like the equal basis because we're done with testing the cubes. Okay? So we change directory to there. So CD and then data whole APNT equal basis. Right? Good. Now we want to see what's in there. The way you do it is you say list, but list is LS for list. Unfortunately, it gives you this, which is a lot. But if you're clever experimentalist or paying attention type of experimentalist, you use LS with a dash and LTR. So it says, give me a list, give me in time order, and by the way, I want you to reverse the time order so the newest ones are at the bottom.
Okay.
And sure enough, we don't care about stuff that was produced in 29, well, maybe we do, but anyway, or stuff that was produced a while ago, we want to know which one was produced last, most recently. And the important part is the part that tells us that the last run number that we took is 8141. You see this? So every time we start the data acquisition and we hope that it's going to save some data for us, that is going to be indexed with a number.
Okay.
That number needs to be continuously increasing.
Got it.
Okay? And as I said, if you make the mistake of giving a number that was already there, it's going to scramble the name and things get a little bit trickier. Still recoverable, but not easy. Right? So the simplest way for us is to do 8142.
Okay.
Right? Good. So now all we have to do now is start the run, and we go once again to user VME, user local VME scripts, and the program is called start_stop. So you start the run and stop the run.
Okay.
All right? Now this program wants 3 parameters, so you need to type 3 more sets of numbers after it before you push enter.
Okay.
The first one is the duration of the run in seconds. So if you want to take data for a minute, you say 60. If you want to do it for an hour, you say 3600. Okay. The next one, oh sorry, I misspoke. The first one is the run number.
Okay.
So 8142 will be first. Second one is what I told you is the duration, right? And then the third one is the delay from the time you put enter till it starts actually taking data. In the past, we were doing for a different project with cubes that had to stay 1 hour with high voltage to get accustomed to the DAQ.
Yeah.
The same way pirates, they were not all missing eyes, they were keeping the patch so they get that eye accustomed to the lack of light below deck. Right, so when they go below deck, they leave this, close this other eye, and then they can see in the dark. Seriously. I mean, I'm not, some of them probably like they're fighting and they lost the eye, but not in the quantities that you see them having patches. Okay, now, that being said, 3 sets of numbers, 8142 we said it's ours. Anything, you've seen the height, right? So the more numbers you get, the bigger the spectrum is going to be in height, because you're doing a frequency table. So these 2 peaks will going to go bigger and bigger the more you take data.
Okay.
For us, anywhere from 2 minutes, 3 minutes is plenty. Okay? So let's say we're aiming for, say, 2 minutes and a half. 2 minutes and a half is 150 and 0. Because we want the result, we don't want any delay because we're not in the situation I described earlier, right? So that's basically it, and I'm going to push enter, start things start happening in the terminals that you already have. And the telltale one that you're looking for is the part that says go count, is telling you the time, and now it's gonna start saying first buffer, second buffer, dump first buffer, this second buffer, and so forth, right? Now here it says when you started, the time on this is skewed, 9:04:57, 9:05:25, so now is probably a good time to start turning the light on,
Oh, okay.
because right now without light. Again, if you are so inclined, I go for it. All right, so now we're injecting light, okay, and it's gonna continue like that till the end. A side project that you might want to be involved with, either or any combination, maybe get Zishan in the discussion as well, is take a little Raspberry Pi, obviously not the one that we're using for the test that Alex is doing, right?
Okay, yeah.
But we haven't. And there is, believe it or not, there is a power strip that has a relay. You can turn it on and off, the whole power strip, with the Raspberry Pi.
Oh.
So then what you do is you connect the light to that power switch, and then you have the Raspberry Pi next to you here, and then you command it to start. When this one starts, count 30 Mississippis, and then turn the light
Yeah.
on. You see what I'm saying?
Mm.
So that's a very nice and self-contained project. And by the way, you can do that with your household appliances, because this power strip is about $20, and a Raspberry Pi you can get as low as $10 for a Pico, and then obviously you can spend more money for bigger ones. And you can turn fans, whatever it is, you can put in that power strip on your own, so you can make like home automation. Right? So that would be something. It saves you a trip, saves you having to remember and such. That would be the idea. So now when the 2 minutes and a half are up, which is gonna be in about 10 seconds or so, I'm looking at that, and I'm looking at the system clock in the corner. Alright. Is going to tell me, so this continues to write data, which is good.
Mm.
So there we go. So it is done. Now, at the end of the data acquisition, it also runs root, and it transforms the data. I will do again the trick with LSLTR. And what do we see? We see that we got the data, something that starts, it's got the number that we want, 8142. It's got some other things, and then 0000. So that's the data. You see that? And then next to it, it's got something that is called exactly the same, but it's got some more stuff, and says .root. That's the one that contains the histograms.
Okay.
See that? And now we can convince ourselves that that is indeed looking good. So we start root. If you start root like this, it's going to have a splash screen that tells you CERN and such. But if you don't want that, we put that and says just welcome to root. T file, F, new T file, and then you say trigger test, and again I'm using this facility extensively, the tabbing. So basically you say T file new, I'll show you how you do it with the browser afterwards, because that might be something more that you might be accustomed to. And I happen to know with the .ls, you see what histograms there are. If we done our job properly, ours is in channel number 6, but because channels are numbered here from 0, it's going to be whatever histogram 5.
Okay.
All right? And it's a matter of QH5. This is a pointer, so you dereference the pointer and you draw it, and it's there.
Okay.
All right?
Okay.
So it looks exactly very nice. It's got a pedestal and it's got a signal that looks not dissimilar to what we've seen yesterday.
So if the base is not working, is it just going to have the pedestal and no signal?
Or it might not have anything.
Okay.
If there is a connection that is not there, like so somebody made a boo-boo when they solder the signal cable, there is no signal.
Okay.
In which case, we can look. What will you see when you put like one of the others that we know they're empty? Right? Yes, you get something, but it's way narrower. You see that?
Okay. Yeah.
right? So that's basically no signal, just electronic noise,
Mhm.
right? So that's not usable, but this is again something that is hanging in the air, it's not doing anything,
Okay.
right?
Okay.
And again, the other order of business, and presumably that is good when you are over there, you smell it, make sure that it doesn't smoke. Because if it smokes, it's not no point in doing this,
Yeah.
right? So if it looks like it's cooking, it's probably not a good idea to continue to power it, right? So that's basically it. The other thing that I was showing you yesterday, and we can look at it. Let's see if I have this editor here, which I do. NP.01. So this is a simple calculation made a long time ago by moi, because it bears my initials. All right, and basically what it does, it produces, it finds the pedestal, so it finds the location of the first peak,
Mhm.
then it gets, all right, so finds the pedestal, and then it fits the second peak with a Gaussian, and it takes the mean and the standard deviation of the Gaussian, and it's gonna produce, let's see what is producing the NPE. Chi-square mean minus fit NPE. So you see it's the signal mean minus the pedestal mean, so it's this difference divided by the sigma of this. So that's the number of photo multiple, well, that's the square root of it, because you see here it's squaring it up. We can go the theory why this is so, but that's right. So that's what this program does, and the way you run it, you say root, and actually it actually produces a thing for you, which is exactly that. It says root with dash Q dash B dash L, so it's basically in batch mode, so we don't have to type anything, and you run that program with the argument, which is the run number that we just done. Okay?
Okay.
So if I either type that or I say source run root, it's telling us all we needed to know, and obviously it does for all the histograms. So this was meant to do mass production of this stuff, right?
Mhm.
For us, since we're doing only one right now, that's the part that is important for us. This is the number of photoelectrons is about 70, and the amplification, which is about 244,000. And then the relative quantum efficiency for this one, you need to have the big photo multiplier powered up, and so that's not going to work for us, but it's not relevant. Okay, so now this one is relevant. If this number is way big, that means the fit is big. So that means that the data doesn't really look like a Gaussian, and you try really hard to make it look like a Gaussian. And yes, you can do the math, but if this number is much above 10, I will not believe it.
Okay.
You see what I'm saying?
Mhm.
But again, presumably you saw that when you look at it. Anyway, oh man, this don't look like it. And then weird things happen, but for this is a reasonably well behaved tube, so I'm short of you destroying it, this should be okay. Alright? So that's it. Unfortunately, this one requires you to do a Control C. So now I promise you that we can do this by hand. Okay, so let's do this. It shows you this is root version 5. Now we're up to root version 6. That doesn't matter. Right? So what you want to do is T browser. All right, and you say, I would say D equals new T browser, and that will bring up a graphical user interface. There we go. You see that? So it's giving us a graphical user interface. Now the problem is, of course, you get everything under the sun here. So you need to scroll your way down to the, whoopsie, where is it? Where is us? It's kind of tiny. 8142 root. Don't try to open the binary files, that's not gonna work. So click, and here are the histograms. Right? Granted, there is way of making the font larger, but here is QH5.
Okay.
Right? So this is basically the same functionality, except with clicking and really knowing what you're looking for, right? Because if I'm doing this, that's again nothing.
Mhm.
And then when you're done with it, you can X out of it right from here.
Okay.
You can X out of it. You will still be in root. How to get out of root if you're stuck? .q quits.
Okay.
So it gives you back the prompt. So this is the end of root, goodbye, and you go back to where you were before.
Cool.
Okay? Does that make sense?
Yeah.
Yeah.
I'm sure you're gonna get stumbled, but like again, don't